All of the problems recorded in my videos can be downloaded at statisticsworkbook.com. If you go to the website, click on the PDF, and you can download a copy of the entire workbook for yourself. Also on the website, you'll find access to all of my videos that I've produced on statistics, not only the ones uploaded to YouTube. I've uploaded over 100 videos that just aren't available on YouTube. So, I hope you'll check out statisticsworkbook.com. Alright, let's begin. Hello and welcome to this next problem here. We're going to be looking at yet another hypothesis test, two population means, and in this exercise again we're going to be assuming that sigma is unknown, so that means we're using sample standard deviations, which if you've watched the preceding video you know that we then have to calculate degrees of freedom, which is a little bit of a cumbersome activity. So we'll cross that bridge when we get there. Let's get into this problem, and I'll talk about it as we go, as usual. Okay, so here we are looking at diversification among students. So we have university classes are becoming increasingly diversified, students moving from all parts of the planet to study in different countries. Imagine your statistics instructor gives you the following assignment. Measure the heights of the students in your class and sort them by continent of origin. Perform a test to determine if the average height of students in North America is different from the average height of students in Europe. As a good student that you are, you awkwardly go around asking your classmates how tall they are. And here's the data that we gather. Okay, so formulate the test, justify the test. Same general procedure for all of these problems. So the first step, put together the null and the alternative hypotheses. This is a two population case, so mu1, mu2, and it does tell us right here that we're doing a two-tailed test. If that information wasn't there, we would have to look for some clues in the problem to identify, are we doing upper tail, lower tail, or two-tailed test? And there's always clues in the problem, and in this clue we would go perform a test to determine if the average height is different. So there's our key word right there. We're just looking to see if there's a difference or not. We're not looking to see is one group of students taller than the other, just seeing if they're different. So that means that this is going to be a two-tailed test. Now, when we're doing a two-tailed test, it becomes a little bit less critical that we put thought into how we define our populations. I'm going to call this my European, and these will be my North American. But really it doesn't change things. You could imagine if I were to switch these around, it doesn't change the nature of the test in the same way that it would for a one-tailed test. If you remember, when we're performing a one-tailed test, whether it's an upper tail or lower tail is entirely dependent on exactly how those terms are defined. Two-tailed test, a little bit less important. So what I'll do here, I'll just rewrite it again, because we're assuming or we're testing for a hypothesized difference of 0. I'm perfectly content writing that hypothesis just like this. So there's my formulation for part A. Justify this. Well, if the evidence supports the null hypotheses, then that supports the claim that there's no difference in average height between these two groups of students. If the evidence supports the alternative hypotheses, then we have evidence to show that there is a difference in average height between these two groups of students. Okay, so we don't have a level of significance. You guys may be getting bored of always doing alpha 0.05. We can do anything else, and in fact, actually, maybe at the end of this problem, we'll change alpha and just see if that makes a difference to our results. So let's move on to part B, calculate our test statistic. So I'm going to actually move down, I'm going to scroll down a little bit. I don't have a lot of room in this exercise. So there I've got all of my all of my data still visible. So this is a t-test because of course we don't have the population standard deviations, and so we're using the sample standard deviations. And so again, it doesn't really matter which way I enter the data, population 1 or population 2. I'll stay consistent with how I've define my terms in the hypothesis test. So Europe will be number 1. So there's my European mean right there in inches. So 71 minus 69 divided by the square root. So this is a standard deviation, so we have to square that. Sometimes the problem might tell us that this is the variance or variation. Let me put variance. And if the problem gives us variance, then we wouldn't square it. You'll notice in the formula, of course, this is squared, but that's the standard deviation squared, which is the variance. So if we were given the variance, if this were the variance, then we wouldn't square it. But in this case, that's not the case. I'm just pointing it out in the event that that ever comes up. So here we have the standard deviation, so we need to square this. Divided by our sample size is 83, plus this one is 4.7 squared over 109. And so what do we get here? Where's my calculator? So I'm going to do the denominator first, just because I find that's easier to do. 83 plus 4.7 squared divided by 109, and square root that. So I get 0.816, let's round it, in the denominator. 816. And the numerator, well, that's just 71 minus 69 is 2. So I'm running out of space here. So this is going to be 2 divided by 0.816. 2.45. 2.45. Okay. So the next step, of course, is a t-test, is now to go and figure out our degrees of freedom. Now this, because we have no reason to assume that the variances are equal, it doesn't tell us anywhere in the data or in the problem to assume that population variances are the same. And so for that reason, we need this big ugly formula that you may have seen once before, s1 squared n1 plus s2 squared n2 all squared divided by 1 over n1 minus 1. S1 squared over n1, all of that squared, and 2 minus 1, oops, S2 squared and 2, and all of that is squared. So this is the tedious calculation. So here I've already, if we remember this denominator, that's this part here, which is very similar to what we have over here. So what I've got in the denominator up there is the square root of this. It's the square root of this piece here. Where's my pen? Right, it's the square root of all of this, which is the same as all of this. So what I need to do for that numerator is just square that piece twice. So if I have 0.816, if I square that, now that's equal to that piece that's under the square root sign, which is exactly the same as the numerator in our degrees of freedom, or it's inside the brackets of the numerator. If I square it again, now I have exactly that numerator value in that degrees of freedom formula. So let's keep it to 4 decimal places, because I think this gets a little bit tedious. So 0.4434. 4434. Now we'll have a big ugly piece down here. I'm going to do this in, I think, 2 steps. So this bottom piece is going to be 6.2 squared divided by 83 squared divided by n minus 1 is 83 minus 1 is 82. So there's that first term is 0.0026 plus, and now this next term is going to be, so that's 4.7 squared divided by 109. All of that is squared, and we divide that by 1 divided by n minus 1 is 108. And so that's 0.0004. Okay, and now we can perform the rest. So 0.4434 divided by 0.0026 plus 0.123004 equals 148. 148. Whew. Okay, tedious calculation just to get the degrees of freedom. So now we have our degrees of freedom for this exercise. I could say our degrees of freedom was 148. Okay, and now we can go look for our test statistic on the t-tables, which we have here is 2.45. So if we go to our t-distribution, degrees of freedom is 148. If we scroll down, well, we don't have 148. The closest we'll have here is 100. And I'm looking for a test statistic that t was 2.45. And so as we move along here, I see 2.45 is somewhere in between here. And so our relevant values are 0.01 and 0.005. And of course, that's just giving us just this upper tail probability. Now, we can't forget, this is a two-tailed test that we're doing, so those probabilities are not our p-values. Our p-value is going to be right somewhere in between double those values. So this is going to be something greater than 0.01 and something less than 0.02. So I'm doubling those values, and they switch sides, of course. So there's the best that we can do as far as our approximation for the p-value. So it's between 0.01 and 0.02. So the p-value less than 0.02, greater than 0.01. And so this now brings us to our conclusion. At the alpha 0.05 level of significance, again, that's our tolerance towards committing a type 1 error. Here we have a p-value that is less than, if I just look at this part, it's less than 0.02. So it must, of course, then be less than 0.05. And so we can comfortably reject. Now, I said before that we can see what happens if we change our level of significance. And so I can see, well, even if we were to do this at the alpha 0.03 level of significance, we would still reject this test. In fact, we would still reject this test if we performed it at the alpha 0.02 level of significance as well. If we were to perform this test at the alpha 0.01 level of significance, now that's going to just completely change our conclusion. Suddenly at that level of significance, we would no longer reject. In other words, we would have insufficient evidence at that level of significance to reject. But let's keep with our original point. So we can change alpha a little bit. It doesn't change the conclusions unless alpha gets too small. So our evidence supports the alternative hypotheses, meaning that yes, there is statistical evidence of a difference in average heights between the European and the North American students. If we continue on with the critical value approach, so we can do that as well, and we're looking for that t distribution, 148 degrees of freedom, and alpha divided by 2 is 0.025. And if we go to our t distribution, alpha 0.025 is there. So that's a critical value of 1.984. 1.984. And again, we get the same conclusion with a test statistic of 2.45. And I have room to draw a little distribution in over here. So there's this distribution. And we'd reject if it's larger than 1.984, and if it's smaller than negative 1.984. Oh, I'm writing just a little bit below. And our test statistic, however, is well out into this upper tail. It's way out here somewhere. So that is in that rejection space. So again, we get the same conclusion as before. Now let's it's not part of the problem. I'm going to actually add a point F, and let's confirm this with a confidence interval estimate. I don't know that we've done one for the t-distribution yet. So let's go through. We're doing this at an alpha 05 level of significance, so that corresponds with a 95% confident interval. So let's just quickly clear up some space here. And you remember we've done, I think it was with the Z distribution, we compared the confidence interval estimate with the hypothesis test. And we can, again, only do this when we're looking at a comparable level of significance. So that's what I calculated here. Alpha 05 corresponds to a 95% confidence level. And only when we're performing a two-tailed test is it fair to compare the confidence interval estimate. So our formula for the interval estimate is very similar to what we've done before. It's that point estimate plus or minus this margin of error, which is S1 squared. It's this same calculation again. Can you guys hear that funny squeaking sound? I don't know if you can hear that squeaking sound. She's got a new stuffy that's got a little squeaker in the belly, and I think she's trying to tear it open and get it out. Okay, so we can just plug in our numbers here. So this point estimate, we've already obtained that, is 2. This critical value, we already have that over here, so this is plus or minus 1.984. And this standard error, well, we've already calculated that too. It's right above here, so this is what we have in the denominator over here, 0.816. So we've already actually done most of the work for this confidence interval. So here the point estimate is in the middle, and let's get the calculator. Oops, I'm hiding myself there. Okay, so this is going to be 1.984 times 0.816. Whoops, there's a mistake in there, I think. 1.984 times 0.816. So that's our margin of error is 1.62. So I'm going to add that to 2. And so I have an upper limit of 3.62. And then if we go for the lower limit, it's going to be 2 minus, oh, I didn't write down the margin of error, 1.986 times 0.816, so 0.38. Okay, so there's that interval estimate. That's a 95% interval estimate. So I'm 95% confident that the true population difference, or the difference in the population means, is between 0.38 and 3.62 inches. Now, we can actually take this a step further because I know how this is calculated. This is European minus North America, and I have all positive values here. So I can actually simply say, well, I'm 95% confident that the average height of the Europeans is between 3.8 and 3.6 inches greater than the average height of the North Americans, rather than just saying the difference in the means is between 0.38 and 3.6. The fact that we know how this is calculated, Europeans minus North Americans, they're all positive values. So I'm 95% confident Europeans, their average height is between 0.38 and 3.6 inches more than the average height of the North American students. Okay, so that's it. That adds point F here. It goes a little bit beyond what we were looking for, but might as well fit in as much as we can. So that's it. Thank you very much for watching, and we'll see you again. Thanks. Bye-bye.